Hey there everyone, it's Alejandro, and welcome back for day 215 and we're doing Daily LeetCode Challenge after it's 1 year's worth of great contributions here on GitHub. So today is promised for February 16th, 2025. Without further ado, let's get straight into it. Okay, today we get LeetCode medium from 1718, construct the lexicographically largest valid sequence. Given an integer n, find a sequence that satisfies all of the following. The integer 1 occurs in the sequence. Okay, each integer between 2 and n occurs twice in the sequence. Every integer I between 2 and n, the distance between two occurrences of I is exactly I. Okay. Twice. So it'll be 2, 2, 3. Okay. The distance between two numbers on the sequence AI and AJ's. Once in the sequence. I see. Holy crap, this is gonna be tough. Oh, n is 20 though. Okay. I see. Okay. Okay. I was about to say, if this is 10 to the 5, this is gonna be really hard to do in linear time. Okay. Yeah, with 20 means we can brute force the heck out of this. Okay. Okay, at least there's that. At least we can brute force the living heck out of this. Okay, a sequence A is lexicographically larger than a sequence B of the same length in the first position where A and B differ. Okay, what I probably want is a frequency mapping of every single substring of n. Wait, n is up to 20. What does it mean, what n? Oh, you want to build the largest sequence. Okay, here put the one between the threes. Okay, in either case, it built the one between the threes. I see, so the answer is going to be fixed for every n up to 20. So you could literally have 20 if statements and keep going until you stop failing, if you really wanted to. Okay, oops, that's not what I want to press. Yeah, although that's a boring solution. I mean, you could try the case where you start with 1, then try the case where you start with 2, then try the case where you start with 3, right? Each integer there's always a solution. Lexicographically largest sequence. Ah, so the order matters. I see. So okay, so you have to have the number 1, and it will be possible to construct every number between 2 and n and have it working. Okay, so the problem will be essentially like, can you find a solution that works with n first, right? Otherwise, if not, can you find a solution that works with n minus 1 first, right? I guess we could probably do some backchecking, right? You just keep going. It's like, okay, you check, like, you know, what is like I spots before you. And if it didn't work, it didn't work. Right? Oh, gosh. Yeah, but this does feel like a backchecking problem. What's 2 to the power 20? Print 2 to the power 20, return empty array. It's 1, 2, 3. 1, 2, 3. Yeah, so it's about 10 to the 6. So yeah, you're probably supposed to do 2 to the 20. Okay, makes sense. You're supposed to backtrack pretty much. Okay. And it's nice, right? Because your decisions are kind of forced. Like either the sequence is already, like, you know, if it's not I in length, then you didn't break any rules. If it isn't, then it's like, oh shoot, you know? Yeah, makes sense. Okay. So here we'll have this. We'll have it as an array. We'll do def backtrack, takes an index I. Maybe the I should be a number, like n, right? So here we'll try something like backtrack of n. Right? Something like that. We'll do if I equals 1, then we'll do res that append. It doesn't matter where you put the 1, right? It just needs to occur once in the sequence. Okay. Do this. If can I do an array is larger than another one? Yeah. Okay. Let me do something like this. Let's open up a terminal. Can I just do a greater than sign and it'll be like Python will understand what I mean by lexicographically largest. Otherwise, we can write code to do it in no event time, but it's just okay, yeah. So it'll just check by okay, perfect. Worst case, you know, you string dot join them, and I know definitely you can compare strings and so on. So it'll be great. Okay, so here we'll do, and it'll always have every single number. Okay, right? Because here, if I did like, you know, if I did 5 here, it should be false. And what about 3 here, right? Yeah. But here, if I do it as 0, yeah, perfect. Okay. If assert the res equals to an n, there's n minus 2 numbers, right? Or no, 1 to n, there's n numbers. So here there's n minus 1. 2 times n minus 1. This is just 2 times n minus 2 plus 1 is just minus 1. Okay, there we go. Okay. Close float. Infinity times. Yeah, okay, fine. We can just make it an empty array. There we go. And largest. We should probably do a copy, right? We don't want it to be by reference. No. Okay, sorry about that. Accidentally opened my system settings there when I wanted to open my terminal. I forgot what I wanted to check. Oh yeah, probably if I do like, you know, tuple this and so on. Okay, yeah. So we can just do, otherwise for now we can just do something like largest equals L for L and rest. There we go. Now we're chilling. It's an O of n deep copy, and he will just return. All right. Yeah. Probably we should do a res.pop. Okay. Anyways, otherwise I doesn't equal 1, which means it's larger, right? Here we should call it num. If num index equals right. Okay, let's think about it. Length of res minus num, which might be negative, but do I need to do minus 1, right? So if if res is 3 elements, and my number is 2, then I'm about to add 2, right? Length of res is 3. So I want to make sure that length of res, which is 3, minus the number, which is, length of res is 3, right? Minus the number 2 and 1. Yeah, it'll get me here. If I wanted to do 3, right? It's like length of res is 3. Yeah, it better be here so that they're 1, 2, 3 apart. Yeah, this is the correct index. If index greater equals 0 and so if index doesn't equal num, they return, right? Invalid case. Then, otherwise, we'll do case 1. Try seeing. Here we can even make it return true. Return false. Right? That way we know when to exit early. We might as well. Here we can even do assert backtrack event. Try seeing if adding largest number Lexicographically yields a correct solution. Or we could even do find the first one that yields the correct solution, right? Yeah, for I in range num 0, -1. If backtrack that depends I num plus 1. No, not num plus 1, num minus 1. This doesn't even make sense. This doesn't even make sense. This doesn't even make sense. Because then where do I place the number? Mate. Maybe I start off with a dictionary of everything I can grab. Line range num 0, -1, where's the depend I? Backtrack of num minus 1. Yeah, it's just not gonna make sense here. It might generally be better to just work with a dictionary. By the way, sorry for the appearance. I went skiing yesterday, and had a great time. But yeah, a little sore, which is also why I'm recording this video a little later than usual too. But yeah, I gotta think here. Yeah, because I need to enforce num, but like, you know, the point is that you might not always be able to really enforce the largest number. So sometimes it's just gonna be like, hey, too bad, so sad, right? So I think that what we need to do is you need to keep track of a dictionary. Yeah. The only thing is just like, I can't make it event per call. I guess it's only 20 numbers max, right? N is 20 at most. So yeah, it's 20 keys. I guess it's not bad on that end. I guess yeah, looping through everything in the dictionary is not terrible. Here we'll say global dict d is equal to comma val for in global dict.items if val greater than 0. Equals 0. Then we'll just say that's our termination case. Largest for L and res, turn true. There we go. There we go. Now we don't need this. No, I don't want to submit. What the heck? Okay. Yeah, we don't need this. Okay. Now what we'll do is, yeah, sorted keys equals sorted keys key equals lambda k first equals true. I don't know. Yeah, by valid. And d.keys are the ones that are valid in the first place. For key and sorted keys. Do I have num anywhere anymore? No, I can use num. Res minus num. And continue. Otherwise, we finally have a valid case. So we're going to try. Try adding number here. We're just going to do return false. Here we'll do res.append number. Def if backtrack return true. Do we even need the returns? Okay. Backtrack. Where's that pop? It might just be something like this, honestly. Yeah, for num, yeah, so okay, for num and sorted keys, yeah. So this is like oh yeah. Here if num doesn't equal 1 and yeah, okay. Yeah. Does equal 1 and res of index. We'll just put the num doesn't equal 1. Yeah. And num doesn't equal 1. Then continue, right? So, okay, I'm being a bit paranoid here. Invalid case. Right? There we go. And yeah, and then at some point, hopefully we'll be chilling. Here we don't necessarily return anything. Here we don't necessarily return anything, we just try everything. Right? backtrack and return the largest. Yeah. Res of the pen num. Global dict of num minus or equal to 1. Backtrack. And then global dict of num plus or equal to 1. Wow. There we go. It's pretty important. Okay, there we go. Unknown network error. Uh-oh. Okay, let me try again. Whoopsies. Unknown network error. Okay, let me try to refresh the page. Okay, this is taking a while. Okay, sorry about that. It seems like there was a gateway 504 server error, which means there was an error on their end, just connecting. So not a worry, everything seems up and running right now. Okay, so we can try running this again. Okay, finally. If res greater than largest, oh gosh, okay. Oh boy. So why can I reach global dict but not largest mate? If anything, I'll call largest, make it equal to self.largest. Oh yeah, I don't need to assert this anymore. This doesn't return a Boolean. Okay. Yep. Okay. We'll do self dot res is equal to self dot res, as well as global dict equals self global dict. There we go. Okay. Oh jeez. Okay. All right. Clearly some stuff going on. Okay, so 3 maps to 1. Now it's just 2 and 2 and 1 and 1. I want to print f string sorted keys equals. At the end of each. Yeah, I'll just do a little print something, just do. There we go. Print a slash n if anything. It just doesn't want to print, eh? Oh, does it just not get to that case? What? Print DSA. What? Oh, because this is the for loop. Yeah. Okay. You'll print the new line up here. Yeah. 3, 2, 1, 3, 2, 1. 2 and 1, 2. I want to print that every single time. This doesn't even make sense. How did it accept this? Okay. Okay. For num and sorted keys. Yeah, it's accepting. It's accepting terrible solutions. Yeah, this isn't even valid. Okay, so I'm doing this wrong. Should this be like -1? It is minus the num. Right, like what I'm trying to check here is like, hey, is it possible to backtrack from this point? It's so like, great. Num and sorted keys. Okay. Yeah, length of self.res, right? So it's like here, like the length will be 3. Which means that, yeah, I'd want index 0 specifically. Yeah, if num doesn't equal 1, and it is the case that index is good, and index doesn't equal num, then I don't want to consider this guy. It's like here, when I got to here, right? The num wasn't 1. Index was 2 minus num. Oh, I see. I see. I see. So I need to check. So instead, instead of this, if num is not 1, value in global should have been 2. However, value is not 2 means this is the second time we select this number. In that case, should be that. Res is not only well defined, but also be exactly the same value. All right, so there we go. Instead of this, it's like if d of num is less than 2 and num doesn't equal 1 and d of num doesn't equal 2, then the second time we select this number, then we'll say index is equal to this. There we go. How about something like that? Still no, huh? Oh gosh, okay, now we're... So now nothing works, eh? Geez, wow, this one was really close at least. Okay, we were interested in the behavior at 3, 1, 2, 3, 2. Right? Okay. 3, 1, 2. Okay, what happened here? 3, 1, 2. It should be minus num. Oh my gosh, okay. There we go. Okay, now we're in accepted territory. Alright, alright. Let's take the prints, let's turn them into hashtag prints. Alright. Okay, and now let's submit. Okay, we might be a little slow. TLE, okay. Oh gosh. Alright, alright. TLE, eh? Damn. Yeah, here we're doing more than 2 to the 20, right? We're doing n to the n. We're doing 20 to the 20. Oh boy. Yeah, we might as well start doing some return trues, right? That way, whenever we find something that's true, we keep it. Yeah, so the right, yeah. It were to return true. Yeah. So here we can assert the backtrack. Success equals backtrack. If successful, don't try anything else here, as it will guaranteed to be lexicographically smaller. Success, break. Okay. Now what's our return false case? Yeah, here we'll just return false by default, right? If everything we exhausted in the for loop and nothing worked, then we'll return false. No number available to us worked. So this is a dead end. Okay, how about something like this? Ooh. That's bad news. Uh-oh. get rid of this case here. Really? Okay, okay. What? Return true. Okay, now we can assert backtrack. Okay, 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 okay. Okay. Now this guy. Oh my gosh. Okay, okay, okay. There we go. Okay, so now that one works. All right. Now are we passing? Are we chilling now? 631 MS is kind of scary, I'm not gonna lie. Okay. If anything. Of the global dict equals 0,1 plus 2 times n minus 1. Right, this will be index 0, index 1. There we go. And oops, I need a self.global dict. Okay. It's a little faster. Not too much faster though. Yeah. Okay, TLE. Yeah, this is just, ugh. Dang. Yeah, that's not the problem. This is at most 20 iterations, right? It's just that, yeah, this kind of hurts. Damn, this really TLEs. Yeah, 20 to the power 20 is a bit too much. Also, yeah, yeah, I need to leave in like max 10 minutes too. Okay. Like, one nice thing is that, like, you know, we could really, we're TLEing on like 11. Really, we could make it, like, once you do half the numbers, you already know the other half, right? Like, they're fixed positions where you need to put them. Right, like, will one ever, like, that's what I'm saying, will one ever be towards the end? Because it's like, it knows where it needs to be. Also, the 1 is always between the 3's here. Where was it between over here? Where was the 1? Oh, the 1 was just at the very end. It's not necessarily between the 3's. Okay. I mean, you know, I could also do something like this. It's like I do what I did in the last video. It's like here I'll just do, here we'll just do LCode, LeetCode 1718.py, pb paste into here. Paste, it's indeed, yeah. So we'll do nano LCode 1718. Here we'll just say saw is equals solution. For I in range, what's n? 1, 20 plus 1. Print f string. N maps to, or yeah, whoops. Can I not do control? Oh gosh. I hate that nano makes me. We'll just do n maps to. Oops. Exit, yes. Now Python 3, 1718.py. This is not defined. sure. We'll just make it so that it just, yeah, we'll just get rid of this, you know, worst case, it's like, yeah, it'll just slowly build the solutions here. And so, yeah, if anything, you know, since I do have to go, it's like I can just like run off and like just let this guy run. And like, you know, worst case, we'll just have like a solution where it's just like, yeah, it'll take a little bit of a hot minute for it to build a solution, but yeah. It's like worst case, I could just have that little script running in the background, and then we'll just like, you know, have a crispy, probably beats 100% MS of solutions, because we'll have everything in there, right? But the only thing is like, you know, if I do something like this, Python 3, 20 to the power 20, it's just, yeah, it's just, I'm not even gonna be able to brute force this. Like, I might as well Control C out of it, but you know what, might as well just let it run, why not? But yeah, it's just not gonna work, especially not in a LeetCode setting. So we do have to think about how we're gonna do this more efficiently. Although I will have to get going soon. Oh, okay. I'll come back and do it. It won't be a problem. It's just, yeah, I came back into my room to quickly do the LeetCode, but I have to check back in at a hotel because the checkout time is at 12 p.m. And I need to get back the hotel key, and I need it's only like 5 minutes away from here. But yeah. Okay. Yep. Yeah, for something like this, yeah. There's the solution for 11. Yippee! But yeah, it's gonna be a little bit too slow, and I can already hear my computer fanning like crazy. Right, it's like the first number, you gotta think of it in positions, right? Like the first number, what's the smallest available index? Yeah, so maybe we think of it in terms of available indices, right? And like the first number, it's like, okay, you want to take available index 0? Okay, you take available index 0, what was your value? Like 10, then like, you know, 0 and the next 10 are now unavailable, right? And then you just keep going. And at any point, it's like, okay, you want to use up this index? Okay, is the other index available? Cool, okay, use it. Otherwise, you can't. And if you do, it's like, okay, try backtracking. If it fails, it fails. Okay, I think, okay, I'll write my idea here. Idea. Do things in terms of available indices. Hence, with n equals 20, have 1 plus times and we have 1 plus 2 times n minus 1. We want to grab and num, speed that plus num are both available. Then keep backtracking. Etc. You will over those chosen indices probably, but that shouldn't be too much of an issue with a dictionary. Smiley face. Okay. Okay, I gotta go. I'll be back, but that way I've at least written this idea so that I can reread it when I come back. So that will be the very next thing that we try. But yeah, I'll also have like, I have this, script little running in the background a little bit. But yeah, it's just like we're never getting through this in a million years. So it's like, I might as well turn it off, but it's like, maybe we get to 12, 13 and so on, but we're not getting to 20. But you know what, for the sake of science, I'll let it running. But I know for I can't even comprehend what number this is. It's just I'm not computing it, right? Like this computer can barely compute like a billion things, right? Let alone whatever this number is over here. So I'll just like, yeah. But for the sake of science, right? I will be right back because I do have to go. But when I come back, we will try this idea right away. So for me, it'll be a little bit of a time, but for you guys, I'll be right back in literally just 1 second. Okay, hey there, I'm back. All right, let's try this idea again. Okay, I'll check in my script. Yeah, okay, we're not even at 12 yet and so on. I might as well just terminate this. We're just not gonna brute force through that thing. Just not even worth it. Okay. Yeah, let's try to do things in terms of available indices, right? So we'll just call this def naive. All right. Self dot naive of n. This is too slow, right? Right. Yeah, 43 ms, but it's just way too slow. Idea: do things in terms of available indices, right? Available indices. A set of actually, range. So if n is equal to 1, is 0 plus 1. If n is equal to 2, we should have 3 indices. 2 minus 1, 2 plus 1, yeah, to 3. Right, this should be good. Which is really 2 times n minus 2 plus 1. 2 times n minus 1. Okay. That's 0, 1, 2, 3, 4. 0, 1, 2, 3, 4, yeah. Okay. Self dot the length of the available indices is 0, we'll say this time copy of the largest okay. Otherwise, okay. And we'll do continue. Okay. Otherwise, try this index. On to next number. Also keep in mind that if k should only check indices occurrences of it. Otherwise, available in stuff.available. Yeah, so if the index, yeah, so we try first indices. Ones are fixed for number. Okay. Not even try index. Even available. Continue. Otherwise, try the index and see if it works. I guess this is enough. Yeah, because otherwise, this is just enough. Like we might as well just Otherwise, try the index and see if it works. Okay. Something like that. Largest index, okay. Probably don't need this. Anyways, let's just try this. Okay. Well, that would explain it. Def backtrack. Wait, is this? There's none of them worked. No. Then we want to just keep trying to the next number, right? So here, we just return false. Now here, do backtrack, insert backtrack, return self the largest, here for self dot add, my bad. gosh, that's bad news. That's really bad news. Does it work with the other two? It doesn't even work with them. I see. There's also the number 1. Alright, we'll just do the oh wait. Continue otherwise. No? Oh gosh. 1, 2, 3, 4. I see. I found a valid solution. I just only found one solution, right? Okay, so we were exiting a little early. But yeah, now we're at 19 ms, which is kind of concerning. Okay, first of all, yeah, let's just see which one we TLE. We probably TLE something. Okay. Jeez, now we're TLEing stuff that's even smaller. Okay. Wait, what did I change from earlier? This. Yeah, so what about this? Yeah, what we should do right, exactly. If I use this test case, 3ms, what if I do n equals 9? 155 is still better than before. 11. Yeah, it starts getting a little tight, eh? Yeah, that's 7.2k. When it's gonna be n equals 20, it's gonna be too much. Okay. We could also just do like, you know, something available nums. I mean, it's like, it's at most 20 iterations. It's like, I guess like, you know, multiplying 20 every time, it can be a lot, so. Yeah. At least this seems to be faster than the previous one, so there's that. We could also make self-dot available a min heap. Alright, let's do that. Yep. This is the problem, right? We need to remove and add an O of one time. Yeah, we can't make it a min heap. Right. Okay. Now what about something like this? Ooh, okay, now we're at 0 ms with these guys. Wait, is this enough? 11. Ooh, okay. Did we just crack the code? Assert, backtrack. Okay, let's submit. And there we go. Completion streak 215 days. Consistency is key. See ya tomorrow. Oh, goodness. Okay, that feels good. That feels good. Finally cracked this little bastard. Jeez, okay. That took a little bit of a hot minute, not gonna lie. Okay. Whew. Oh yeah, we have our naive. We have another backtracking one. Okay. Yeah. Okay. Does this work as well? Alright, nice. Now what if I did self.largest equals res? Does it keep the reference to that? Not quite, it seems. Okay. No worries, no worries, no worries. Let's relax, let's relax. Okay. I'll call this self.available indices. Okay. This is just taking a sweet time here. Did I just break LeetCode? Maybe that's a vulnerability in LeetCode. It tries to run code where it's accessing pointers it's not supposed to. Uh-oh. It's hacking time. Oh no, not unknown network error again, please. Okay, there we go. Now we're chilling. We are chilling. Alright, like this works. Yeah, we're at 10 ms now. Yeah, the minimum of the available indices. N is equal to 1. Yeah. Otherwise, yep. Special case is only takes up one index. There we go. Yep, this we can get rid of. This is a good check, right? Just needed one too. Oh yeah, because otherwise it might not be in there, and so yeah. Love it. It's just a double purpose thing. This. Now we don't have to make these asserts anymore. We could really even probably paste this up here. Yeah. Like if backtrack, true. These guys. Problem statement guarantees a solution exists. There we go, so we're asserted. I don't need to assert it. Backtrack. Yeah, well, we might as well leave the comments. Doesn't hurt. There we go, asserts. Oh, they're in the naive code, eh? Yeah. Okay. Oh, my eyes. Ouch. Okay. Yeah, now we're chilling, right? Okay, submit. Okay, 9 ms with 21.32%. Bada bing, bada boom. Oh yeah, here we can just do the same thing. If backtrack. True. There we go. Yeah, okay, so 13 ms. We're kind of like hovering around this line. I guess the standard deviation is closer to here, so I'm doing some things a little inefficiently. Like for example with this, I could make this a little bit better, right? Here we could just do available nums is equal to set h1 to n plus 1, right? And so here we could just do we could do for right, and then instead of this we could do num and sorted available nums verse equals true. Right. That's like for each of these we could just do something available right? Something like that. Where? Yeah, so like that might make things like, you know, a tiny bit faster maybe. Or not even, right? We're still at that like 11 ms range, right? But that way it's like, you know, I don't have to like go from n to 0 and so yeah, okay, so it's just, it doesn't even really matter all that much. You might as well keep it the same way. Yeah, so like these are not the things that matter too much. Yeah, we can get rid of self-available nums. That was a good change right there though. There we go. Okay, so yeah, we're kind of in this area. There we go. Bada bing, bada boom. Very, very nice. Okay, so as always in my videos, I do a quick recap if I was able to solve the problems. For this one, essentially the name of the game for me was backtracking, just because it's like, you know, n is between 1 and 20 over here. And the point is that we want to return the lexicographically largest sequence, where essentially we're given an integer n, and we must have every single number from 1 to n inclusive, right? But every single number between 2 and n inclusive will occur twice in the sequence. And it must be that the distance, so for each number between 2 and n, they occur twice, but it must be that the distance of each number inside of this, like for example, the number 5, right? It must be that they both occur, but that they're exactly 5 indices apart, right? So it's like, you know, the distance between any two numbers, ai and aj, is the absolute difference of their indices j minus I, and it must be that the distance between any two numbers I between 2 and n is exactly I, right? For example, in this example, the numbers 3 are 1, 2, 3 indices apart. The numbers 2 are 1, 2 indices apart. The only special exception is the number 1, right? The number 1 is the only exception itself, right? And so essentially, what I did is that, well, the very first thing that like all of my initial ideas were not working, where essentially it's like, you know, I wanted to figure out like, you know, where I can put an where I cannot, and so on. And so, yeah, I have a lot of this logic that I was trying, which wasn't really working. So I'll just focus on probably what is the most important part, which is what I did that actually did work. And what I did that actually did work was actually focusing on the available indices, right? Because it's more important to focus on the fact that if you choose a number, like say the number 5, well, as long as you focus on, let's say, the earliest occurring index of that number 5, right? The next index is kind of fixed for you, right? Because it'll be like, you know, if number 5 goes at index I, then you know that at index I plus 5, you'll also need the number 5, right? So you can kind of cut down half the search space just by realizing that, like, hey, for any number, I can just focus on, like, you know, what is the leftmost index it should be put at? And like, you know, the rightmost and the right index of that same number will be kind of fixed for me already, right? So what I did is essentially, I'm going to have like, you know, a self.largest, which will be like, you know, used for my actual lexicographically largest result. So it'll be my, you know, actual result. Then I'll have, you know, a set of available indices. Originally, so, you know, I'll have the number 1. And then for each number from 2 to n, of which there's n minus 1 numbers, we'll take up 2 indices, right? So it'll be 2 times n minus 1. Then plus 1 for the value 1 total indices, right? Then if you take this, it'll be 2 times n minus 2, negative 2 plus 1 is minus 1. So that's why I have 2 times n minus 1 total indices, right? So it'll be a set of each of those indices, right? So it'll be 0, 1, 2, 3, all the way up to 2 times n minus 1, right? And then I'll have a dictionary which will map numbers to their mapped indices, because the point is I'm going to essentially backtrack to essentially find every single possible result that I can, and as I backtrack, I'm going to keep track of, like, you know, the indices that a number belongs at, right? Because I'm going to figure out, okay, like, you know, can I put the number 5 at index 3? If I put it at index 3, okay, let's try that, which means that the number 5 will go at index 3 and index 3 plus 5, which is index 8, and be like, okay, so the number 5 is mapped to indices 3 and 8, which means, like, you know, as I keep backtracking, I can't use indices 3 and 8, and so on, etc., 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 right? So I just map numbers to indices. And then I have a backtrack function, and the end result is like, okay, when there's no available indices left, that means that's like, you know, you found a valid goal end state and so on, so things are good. So, you know, check if it's a better solution, right? So we'll build an array. It'll have 2 times n minus 1 total indices again. So I just put 0 values in there for now. And then remember, we have a dictionary that maps numbers to their indices, right? So for every single, like, you know, number and indices pair in self.d.items, I'm going to say, okay, for every index inside of those indices, I'm going to say res of index is equal to that number, right? Essentially, inside of my dictionary, again, we map a number to the indices. So for each of those indices inside of my result array, I'm going to set that the value of that index to that number, right? And then I'm going to say, okay, if the res array is larger lexicographically than my current self.largest, which is initially empty, so it'll always be smaller than anything else, then I'm going to set self.largest to a copy of the result because it is a better result than what we currently have in self.largest, right? And here I'll return true just to denote like, hey, we found a valid solution here, right? It'll be important later on, right? Otherwise, if we have at least still one available index left for us, then what we're going to do, essentially the idea is as follows. We're going to grab the smallest available index to us, right? Because we have to fill in every single index no matter what, right? Sorry, by the way, my eyes really hurt from looking at screens, so I might do a bit of things with my eyes closed and so on. But please forgive me. Okay. Length of self-available indices. Yeah, so we covered that case. Then the idea is that, okay, based off our available indices, we have to fill in a number at every single index, right? So we might as well figure out, okay, what's the number we should put at the earliest index, right? Because again, with lexicographically largest, we want to, essentially put the largest numbers at the beginning. And like, even if you have something like, 2,9876543 this is still bigger than 4, 5, 6, 7, 8, 9. Sorry. What I want to do. Here we'll do. Okay, this is what I'm trying to show, right? Something like this, even though it's like, most of the numbers are like, smaller than their counterparts, right? Like 3 is smaller than 8, 4 is smaller than 7, 5 is smaller than 6. The first number here is a 2, which is bigger than 1. Therefore, this is lexicographically larger, right? Too bad, so sad. So you really want to put like the biggest numbers that you can at the very beginning because they'll have a weight and influence for everything else, right? So out of all the available indices, we have to fill them anyway. So we might as well figure out what's the one we should fill with the smallest available index available to us, right? So we'll take the smallest available index to us, right? I might as well put this over here, right? There we go. Oh, that might actually also be one way to do things a little bit faster. Oh yeah, now we're at 8 ms, right? Instead of recomputing the min every single time. Oh yeah, this does not apply anymore. Well, we need to fill in every available index, so we might as well number we can put in smallest available that will have the largest impact on how lexicographically large a result will be. There we go. Okay, sweet. Sorry. So that's kind of the point, right? We're essentially going to focus on just one index. Okay, and nice. And now we're close to that 47%. So it's just like, small over one stuff. Not too major or critical here, right? But the point is essentially that, right? And then, so we'll focus on just the smallest index, right? That'll have the largest impact on our result being lexicographically as large as possible. So we might as well just focus on it, right? We have to fill in every available index. We might as well take the smallest one and be like, okay, what's the largest number we can effectively put in there, right? And so that's exactly what we'll do. We'll loop through every single number from the biggest one, from n all the way down to 1, right? So 0 not inclusive, so it'll go down to 1 and backwards, right? So from like, the biggest number available to us down to the smallest, right? And we'll put whatever the biggest number we can possibly put in here, right? Because that'll have the biggest effect on the lexicographically largest, right? And as soon as we find like, a valid number that works, that's the largest number we can put, we'll essentially short circuit, right? Which is why we'll return true here, because that way it's like, whenever we see like, if we're able to backtrack and it's a good result, then we'll return true because we put the largest possible number we could have put in this index, which will make like, the rest of the things as like lexicographically large as possible, right? That's kind of the point. So, but again, like we keep going. So first of all, for every single number, if the number is already, mapped to some indices, then that means it's already mapped to some indices. I can't, remap it again, right? Like I already have like, two positions where I put the number n, for example, let's say, then I can't do the number n, right? So it's like, I already paired this number with indices, so ignore it, we just continue, right? So we're gonna loop through from largest to smallest, but obviously we're gonna ignore things that already have a setting in it, right? So that is kind of the point. Otherwise, okay, so once we kept looping through this for loop, if we ever break past this condition, then okay, finally we have a number that's not in our self.dictionary, which essentially maps numbers to the indices that they've been allotted at. And so it's like, okay, let's figure out where to put it. Now, there's one special case, which is if the number is 1, right? Because if the number is 1, it does not have 2 occurrences, it has just 1 occurrence, right? So here we'll just say, okay, self.d, we're going to map this number not to well, it's still going to be a tuple or array of indices, but now it'll just have one element, it'll be the index itself, and we're going to remove that index from our available indices because we're going to put the number inside of there. Then we're going to try backtracking. If it works, then great. That's exactly what we're just going to return true because this is the best possible solution that we can do, right? Even though the number is 1, it'll probably be the only possible solution that we can do. But that doesn't matter. And so yeah, if like again, at any single point in here, if we figure out that we can backtrack with a certain number, it's the biggest number that was available to us, right? And so here in the case, it's like 1 is just like it'll conveniently be like the very last case, but oh well. But yeah, if it's true, then just return true. Anyways, otherwise, like, if the backtracking didn't work, in this case, it has to work. So I could really just do something like, what I could do is this. What I really am trying to say is that I could assert that backtracking will work, right? And if I submit here, I bet you it'll still work. Really now. How could I get to the last number and it would not work? What? Okay, that's confusing me. I'd have to think. Because that'll be the last number I look at, so nothing else worked. Well, I guess because in other cases I have a okay, never mind. Again, that's the dangers of backtracking. Yeah, because it might be in other cases where it's nested instead of another like set of backtrack calls and so okay, yeah. Forget what I said. Forget what I said. Yeah. Okay. Sometimes forget everything. When you're backtracking, everything matters with everything. Okay. All right. So yeah. So just simple case, if we're able to backtrack, this is the best number that was available to us, and so on. Because again, we're looping through all the numbers in backwards order and finding the very first one that works. If it happens to be 1, so be it. So if it's possible to backtrack, then we return true. Bada bing, bada boom. Very nice and clear-cut solution. Okay. Otherwise, what we're gonna do is okay, if the backtracking failed, not a problem in the world. We're just gonna delete that from our dictionary mappings, right? So we'll no longer have the number mapped to the indices that I mapped to. In this case, it's just one index. We'll add the index back into the set of available indices, and then we'll just continue from there, right? Otherwise, if the number wasn't 1, it'll essentially be the same thing. It's just that now there will be 2 indices at play, right? It'll be index and index plus num, right? Because again, for every integer I between 2 and n, the distance between 2 occurrences of I is exactly I. It must be the case that this is true, right? For example, 3, it must be that they're 1, 2, 3 apart. Both of these 3. The 2s are 1, 2 apart, etc., right? So again, we're going to focus on only the leftmost occurrences of indices, right? That's where it's going to be lexicographically largest impact. And that way it's if we say number 5 goes at index 3, then we already know, okay, the other 5 must be at index 8, right? So it's already kind of sit and fixed for us, right? So what we'll do is, okay, first of all, if index plus num is not in the available indices, that's okay, if we were to pick this index, we don't even have the other available index that we know our number must be at. Therefore, it's we can completely ignore this case, right? We might as well just not even try, right? Otherwise, okay, both index, index is available because we just grabbed it from our available indices. But otherwise, if index plus num is also in our available indices, then we might as well try it. So we'll map number to both index and index plus num, right? Index plus num is kind of fixed for us. And we'll remove both of these indices from our available indices. We're gonna try backtracking. If it was successful, we will return true because again, we just tried the biggest possible number that was available to us and it worked, so we will return true, right? Even if, as before, we ended up with a case like this where most of the numbers are smaller than here, doesn't matter, this number is bigger than this one, therefore this entire array is lexicographically larger than this one, right? That is kind of the point that I'm trying to make here. And so yeah, okay, so yeah, so yeah, okay, that's why we return true early if we can. Otherwise, it's okay, if the backtracking didn't work, then we're gonna probably end up having to try a smaller number, right? So let's refix our backtracking setup again. So let's remove the number mappings that we put in before over here. Let's add these indices back into our available indices and not immediately return false, but rather keep trying more numbers, right? Otherwise, if we tried every single number and none of them worked, then we will return false, right? Which is why, again, I can't like necessarily assert the backtracking will be true here, right? It could be false, and it's like, I return false. It's like, oh, okay, I tried putting like, the number n at the, like, index 0, and it got me to a point where eventually I hit a dead end, which means like, I might end up having to backtrack and be like, I can't put number n at index 0 and so on, so try something else, blah, 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 right? That's why I couldn't put like, the return true over here. And so yeah, so if none of those numbers worked, they will return false and say, hey, you hit a dead end, you got too greedy, you cannot go through here, right? So that's kind of the point, right? Otherwise, as soon as we find a valid solution, boom, we're done, and there we go, right? And then that's the entire backtracking function, right? So I just initially called backtrack where I have like, all the available indices available to me, no numbers mapped to anything, and like, no largest value, so on. So I called backtrack with all that initial setup, and then I returned like, the largest array that was ever found, because every single time that I hit a termination case, I append largest to be essentially the largest between the current value of self.largest and the current result value, right? So it's like, create a new array for every single like, num to index mappings inside of self.d, like, let's set res of index to that number, and like, okay, if res is lexicographically larger than self.largest, then self.largest to a copy of res, otherwise, keep self.largest as it is, and obviously return true to signify like, hey, this is a valid termination case you just entered, there was no available indices left, and like, we only take off available indices if we can, etc., etc., etc. You hit a valid case, so return true, right? That way in any of these, whenever we backtrack, we can say, oh, if we return true, then there we go, chop chop, we're done with our work, right? And that is kind of the idea. And then this naive is like, essentially it's also backchecking. This is also a correct solution. It's just way too slow. I'd have to remind myself what I was doing over here. Sort of keys. Oh yeah, essentially I was trying to put like, the largest number first, and if that didn't work, I tried another one and so on, but it just ended up being too slow. Going down the route of available indices, at least it, like, it use the idea that the fact like, if I know that number 5 is at index 3, then I know it's a number at index 8 as well, right? So that way I don't have to like, consider absolutely everything all the time, right? So that it kind of like reduced everything in half, but since it's like, exponential, like, 2 to the n versus 2 to the n over 2 is like, a huge difference kind of a thing, right? But it might be even, I think it might be more expensive than that, but yeah, so we can just get rid of that naive solution. Doesn't really help out much at all, and we could just submit this guy one more time. There we go. Yeah, so like, we might be a little bit slow. We will get like 7% sometimes, like a little less, a little more sometimes. But yeah, we have a reasonably efficient solution. We're kind of dead end in the middle of the pack over here, so pretty happy about it, but that's pretty much it in terms of how I was able to solve the problem. Just some regular old backtracking, but it took a little bit of trial and error. At the end of the day, what worked for me is just keeping track of available indices and focusing on like, the leftmost index that I can essentially shove every number that I can, right? I try the largest numbers first. If I hit a dead end, okay, I can't. Otherwise, if I try the largest number and it worked, then I'll immediately return true and essentially just return the largest thing that I find. Call backtrack once, return the largest result I had. There we go. Bada bing, bada boom. That is pretty much it for how I was able to solve this problem. And yeah, but otherwise, that's pretty much it for this video. If you did find it useful and enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment. Well, otherwise, I'll catch you next one. So until then, ciao, ciao, my friend. Bye-bye.